When protons change, that changes the name of the atom. But we can have atoms that have the same number of protons with a different number of neutrons, and we call those different isotopes. So we could have something like uranium-235 versus uranium-238. Both of these are defined as uranium atoms because they have 92 protons, but they have different mass numbers because they have a different number of neutrons. So 235 minus 92 tells me that uranium-235 has 143 neutrons, and 238 minus 92 tells me that uranium-238 has 146 neutrons. Why does it matter? Why do we care about different isotopes? Well, one of those is radioactive and can be weaponized, and we can make, nuclear weapons out of it. We could use it as fuel for a nuclear reactor. One of them, not so much, right? They actually both are technically radioactive, but one is way more radioactive than the other. Okay. If we're looking at different types of atomic symbols, right? What we're going to do in this class, what we're going to do in any chemistry class, is you're not going to use the name of the chemical or the name of the atom over and over and over again, because nobody wants to write all that down. So we're going to use the chemical symbol or the atomic symbol for that thing. And that's typically either one letter or two letters. The first letter is always capitalized, and if there's a second letter, it's always lowercase. And you can see these on the periodic table. There's a periodic table in the Getting Started materials on Canvas if you don't have one already. There's also, if you open the ebook, front cover of the ebook would be a periodic table as well. Okay? I'm not going to ask you to memorize a periodic table, but you are going to get intimately familiar with the symbols and the masses and all that stuff on there through the work that you're going to do in this class. Okay? So, this is one of the ways that we can show what an atom is. It's something like this. You can see that we have a chemical symbol here, and that can be different depending on what the atom is. We have the atomic number. The atomic number is the number of protons in that atom. And then we have something called the mass number. And the mass number is a whole number. And it's the sum. It's the number of protons and neutrons added up inside this particular atom type. Okay? That's different. If you look at a periodic table, the periodic table doesn't have whole numbers for the mass. They're decimal numbers. They usually go out 2, maybe 3 decimal places. That's a different thing. That's the atomic mass. And that's different than the mass number. All right? So those things are similarly named, but they mean different things. The mass number, given symbol A here, is the number of protons and neutrons added together. Right? And so you can see that over here. Look at this. We call this right here carbon-12. Right? So the name of the atom and then the mass number. So carbon-12. You can see in carbon-12 there's 6 protons. That's how we define it as a carbon, because there's 6 protons. You tell me how many neutrons would carbon have there? Well, 6. It's the total neutrons and protons, which is 12, minus the number of protons, gives us 6 neutrons, right? Pretty simple. And it's also right there, right? If our atom is not charged, then it has to have the same number of electrons as it has protons. So a piece of neutral matter would have the same number of protons and electrons, right? So if this is carbon, carbon's got 6 protons. It also has 6 electrons, okay? Same thing with oxygen down there. We define it as oxygen because it's got 8 protons. This is oxygen 16, so it also has 8 neutrons. 16 minus 8 is 8. And it will have 8 electrons because the number of protons and electrons have to be the same if there's not a charge. Okay, so we talked about atomic number. That's protons. We change protons, we change atomic number, we change the element that we're dealing with. We change the number of neutrons, we change the isotope, right? So we change the mass of that particular element. If we change the number of electrons, then we're creating things called ions, right? So we got 3 subatomic particles, protons, neutrons, electrons. Altering those gives us different things, right? So we alter protons, we change the type of element We alter neutrons, we change the isotope. We alter electrons, we make ions. So lots and lots of chemical reactions are going to be electron transfer reactions, where electrons are going to move from one thing to another. When they do that, we're going to make ions. When we have positive ions, we call them cations. And when we have negative ions, we call them anions. We usually see that written in the upper right-hand corner of our symbol. So if I see something like this, Mg 2+. This is a magnesium ion, and that 2+ tells me that I've lost 2 electrons, right? Remember, electrons are negatively charged. Somebody look at a periodic table and tell me what is the atomic number for magnesium. Yeah, it's 12. All right, so this is atomic number 12, which means that there are 12 protons. And in a normal magnesium atom, there would be 12 electrons. But in this one, there are 10 electrons. So 12 protons minus 10 electrons gives me 2. Protons are positively charged, so there's 2 extra positive charge there, right? So that charge tells me the imbalance between protons and electrons. If it's a positive charge, there's more protons than electrons. If there's a negative charge, there's more electrons than protons. So if we have a lithium atom has 3 electrons. If it gives up an electron, it becomes a lithium plus, because now it has 3 protons and 2 electrons, right? You can always determine the ion charge from protons minus electrons, like I did on the previous slide, okay? In this case, lithium plus got 3 protons, 2 electrons, so it has a 1 positive charge there. Anions work the same way. If I have something like F minus, okay? This is a fluoride ion. What is the atomic number for fluorine? Grab a periodic table and let's take a look at that. 9, right? So that means that a fluorine atom has 9 protons, right? But this minus right here means I've got an extra electron. So in this particular case, I got 9 protons and 10 electrons. And we can double check that. If we go 9 minus 10, that's minus 1. And that's the charge I'm seeing up there. So let's see if we can sort this out. Make sure we understand what's going on here. So I got a magnesium ion with 10 electrons. Well, we just did that one, right? Let's do sulfur with 18 electrons. Let's see if we can sort out what the charge would be on this one here. So we would need to go to the periodic table. We find sulfur. Sulfur has a symbol of S. What is the atomic number for sulfur? 16. So there's 16 protons, and they're telling me here 18 electrons. So what charge should this sulfur have? Should be -2. When we write these, though, we always write the magnitude of the charge first and the sign of the charge last, okay? So yes, it's -2 when we do the math down here, but we're going to write it up there as 2 minus, or we'd write 2 plus for the magnesium, okay? All right, how about iron with 23? So we need to look up iron. Iron symbol is Fe. 26 protons, 23 electrons. And so what is the difference here? That's 3. So how do I write that on the iron? That's right, 3 plus. So there's something called valence electrons. As we learn more about electrons, we'll learn those are the electrons in the outermost shell of that atom. So think about the solar system again. Think about that model for protons, neutrons, and electrons. So protons and neutrons are the sun. We got those different planets. Those different planets are different orbits around the sun, right? So the outermost one would be the valence shell, okay? And so there are electrons that are way out there. If we look at a periodic table, in any of the main group stuff, so any of the ones that have a letter A, 1A, 2A, 3A, 4A, 5A, 6A, 7A, whatever, gives us the number of valence electrons for everything in that column, right? So if I go and I look at the halogens, for example, all those halogens are in group 7A, so I know that all those halogens have 7 electrons in their outermost shell, okay? If I look at group 1, right, lithium, that and sodium, those, they all have 1 electron in their outermost shell. So that number means something, that group number on the periodic table. We can predict what charge an atom is going to get by looking at that and then looking at its closest noble gas. What's the closest noble gas to this thing that I care about? And then, do I need to gain an electron or lose an electron, and how many, in order to look like the noble gas? Right? So let me see if I can show you what I mean by that. So over here, I'm going to fill this in a little bit here. So this is helium. What's next going down the table here? Anybody know? Should be neon. So all of these have 8 electrons in their outer shell, right? But the easiest way to think about this is just find one of the atoms that you care about. So let's look at chlorine, for example. Chlorine has 7 electrons in its outer shell. The closest noble gas to it is argon, that has 8 electrons in its outer shell. So if chlorine can gain 1 additional electron, then it looks like argon, right? It has the same electrons in the outside as argon does. Does that make sense? Lithium over here has 3. Well, it has 1 in its outer shell. So for these over here, the closest noble gas to them is not this one. It's going backwards a step, right? So if we go backwards 1 step, then we look like helium, okay? So these will go backwards 1 step, and that's why you see the plus over there. They're losing 1 electron so that they can look like the previous one, okay? It's a little more clear if we were to actually write their atomic number over here. So the atomic number for helium is 2. You agree with that? The atomic number for neon here is 10. The atomic number for this one, argon, is what? 18. And then say again, 36. Okay, so sodium over here has atomic number 11, right? That means it has 11 protons, means it has 11 electrons. So in order to look like neon, it needs to get rid of an electron, right? And that's why we see this plus. It's because it has lost the electron, so it can look like this thing over here. That's the basic idea. We'll talk about why that stuff works in a later chapter, but this is the basics of it, okay? If you can find a periodic table and you can say, what's the closest noble gas to the thing I care about, then you can determine what charge it would have to look like that. And honestly, what I do when I get a periodic table, +1, +2, +3. This one's questionable, so plus or minus 4, -3, -2, -1, and 0. Those are the charges we're going to make. Is it perfect? No. Is it really close to perfect? Yes. We can always ballpark it with that, okay?